I am Germà from the University of Girona, from the research group of Statistics, Econometrics and Health. This is in the faculty building of Economics and Business Studies. And what I am going to present is already in press, is already an electronic publication ahead of print, with the same title, Analyzing Pairwise Logratios Revisited. The title which was announced previously was slightly different, but this is the correct one. And while it has been published in Mathematical Geosciences, and the first author is Karel Chron, and the rest of the co-authors are myself, Peter Schulz-Moser, Javier Palarial Valadejo, Martin Famara, and Tomás Matiz Grigar. I thank them also for giving me permission to present this here today. So, the backbone of compositional data analysis is what we normally call the Aitchison geometry. This geometry acknowledges the fact that D-part composition has a D-1 dimensionality, and also some important properties like scale invariance. One great development within Aitchison geometry has been the development of coordinates with an orthonormal basis. This provides an isometric mapping between the Euclidean real space and the simplex, and it respects the dimensionality of compositional data. At the beginning, they were called isometric log ratio coordinates, but recently, Martin Fernandez advocated a new name, orthonormal log ratio coordinates, because this name, in a way, reflects better the essential property of these coordinates, orthonormality. We say this because other well-known log ratio transformations, centered log ratios, were also isometric, but they are not orthogonal, and they do not respect the dimensionality of compositional data either. Well, an important aspect within orthonormal coordinates, we will use this name throughout the presentation, is how interpretable they are. Not in all cases is interpretation easy. For this purpose, Egozco and Pawlowski-Glano proposed balanced coordinates. They are a specific case of orthonormal log ratios, which are interpretable in terms of balances between two groups of parts. They are actually the log ratio of the geometric mean of a group of parts over the geometric mean of another group of parts. But still, there are some difficulties. You need to group the parts meaningfully in some way. This is what we call the sequential binary partition. Even if you choose the sequential binary partition carefully, it can happen that some of the coordinates are not easy to interpret. And the connection with individual parts is normally lost. Remember that these coordinates have geometric means of parts and not always individual parts. To address this last difficulty, pivot log ratio coordinates were proposed by Fischerova and Chron in 2019. They are again a particular case of balances, so a particular case of orthonormal coordinates, but special ones. They have just one part in the numerator. And so this coordinate hopefully gives information about the importance of that part within the composition. Even in this way, pivot coordinates are not always accepted. As in some areas of research, researchers are used to employing one of the parts as normalizing a part to which all other parts are compared. So they are interested in log ratios between each part and that normalizing part. This is well known. This is what we call additive log ratio coordinates. They are not orthonormal, they are oblique, but they respect the d-1 dimensionality. And the interpretation is normally very easy because it's just a ratio of two parts. So interpretation is what happens with when one part is reduced and one part is increased, or when the ratio of one part to the other is changed. And this is easy to generalize. You can do a permutation of parts, and then you use another part as normalizing part, and so potentially you can compute any possible log ratio between any possible pair of components. And this is what is called in general terms pairwise log ratios. But of course, if we do this, we once more fail to respect the dimensionality of compositional data. If we want to obtain pairwise log ratios and respect the dimensionality, we have to do some sort of selection. We cannot use all d times d-1 log ratios. Greenacre in 2018 proposed a stepwise selection procedure to take at most d-1 pairwise log ratios, in some cases less, with the aim of explaining as much variability as possible. And hopefully get log ratios which represent leading properties in the data. However, these log ratio coordinates do not mean the orthonormality criterion either. But they are simple, and so that there has been a spirited discussion regarding what is more important, simplicity of interpretation or orthonormality. Even this discussion has put the question if orthonormality is really needed at all, or is just a sort of a statistical refinement only for, say, purists, and should be dispensed with in favor of the simpler interpretation. Well, the answer depends on the circumstances. For some statistical methods, it's really not a problem to have oblique coordinates. Specifically for statistical methods that are invariant to affine transformations. Basically, scaling and rotation. However, not all methods have this property. In particular, methods that are based on distances, like principal component analysis or cluster analysis, do not have this property. As we will see in this presentation, there is also a problem with regression coefficients when the composition plays the role of explanatory variable. Oblique coordinates also violate the subcompositional dominance property, and well, it was a little bit implicit in what we said already. Distances change with the choice of oblique coordinates. But do we have to choose between the simple interpretation of pairwise logratios and orthonormality? Our point in this article is that no, that we can have both. The goal of this article is to show that we can interpret the results in terms of pairwise logratios without sacrificing orthonormality. The idea is to build coordinate systems around a pairwise logratio. So let the pairwise logratio be one of the coordinates in an orthonormal coordinate system. Actually, this is quite useful. Quite usual. Sorry. Normally, an orthonormal system has some balances between only pairs of parts. So what is new is that we focus our attention on those. And another issue is that we rerun the analysis, or we can rerun the analysis several times. Each time we have one pairwise logratio which is of interest to the researcher. We build an orthonormal basis around it. We run the analysis, and we interpret the results of the pairwise logratio, which is the part of the analysis we are interested in. Then we select another pairwise logratio which we find interesting. Again, we build an orthonormal basis around it, and again we rerun the analysis with the new pairwise logratio, and we interpret the pairwise logratio. So we have rerun the analysis several times with as many pairwise logratios as are interesting to us, d-1, or less, or more, or just one, or all possible. It doesn't matter. It depends on our interest. So we rerun the analysis as many times as we want, and from each analysis we collect just the results of the pairwise logratio, and we put these results together. So the idea of compiling results from more than one analysis is borrowed from the concept of pivot coordinates, just in a sort of reverse order. We refer to this strategy as backwards pivot coordinates. And in this way, the pairwise logratios, which are used for the analysis, are supported by the properties given by their orthogonal coordinate systems. But well, before showing you what backwards pivot coordinates are, let's start by ordinary pivot coordinates, and even before that, the simplest and the first coordinate system which was suggested, which were additive logratio coordinates, then another very early approach, which was centered logratio coordinates. So let's just start by additive logratios. These are indeed very simple to compute. You just choose one part, whichever you want, as a sort of reference to which all other parts are compared. And so you compute the log ratio between each part and this normalizing part, we will call it normalizing part throughout. Of course, you can have more than one normalizing part, so you can have more than one additive log ratio coordinate systems. But these type of coordinates are well liked, are aligned with geochemical practice, because very often there is a justified normalizing element. They are still a particular case of pairwise log ratios, and by permuting the components, you could compute any pairwise log ratio you would like. But unfortunately, they are oblique. So, actually, there are two simple ways of interpreting compositional data. The trade-off between just two parts. What happens when you increase one part at the expense of reducing another? And this is what pairwise log ratios do. Another simple way of interpreting compositional data is asking yourself a question: what happens if I increase a part at the expense of reducing all others? And this is what centered log ratios do, because they are just the logarithm of the ratio of one part over the geometric mean of all. So the effect of increasing one part at the expense of reducing all parts. Then original components are linked to the log ratios. Each log ratio can be interpreted in terms of the part in the numerator, because the denominator is always the same. But again, they are oblique, and they do not respect the dimensionality. We have actually d centered log ratio coefficients, while the dimensionality is d minus 1. So the first time pivot coordinates were proposed, it was just to address these drawbacks of centered log ratio coefficients. Can we have something which is interpretable in the same way as centered log ratio coefficients, based on orthonormality and with the proper dimensionality? So these were the first and genuine pivot coordinates. So what do we do actually? Maybe the easiest way to see it is to start by seeing the sequential binary partition. We take in the first coordinate the balance between one part and all the others. Which part? Any, by permutation. So we can have a permuted composition, X superscript L, in which part L is in the first position. And so when we apply this sequential binary partition, in the first coordinate, we will have the balance between part L and the remaining parts. What comes next is irrelevant as long as it is orthonormal, but usually the second coordinate balances the second part with the rest, the third coordinate balances the third part with the rest, until the last coordinate, which balances the part before the last and the last part. So the final coordinate is actually a pairwise log ratio of only two parts. Well, this is just to show that really these pivots are related to the centered log ratio coefficients. Actually, they are just a scaling of the centered log ratio coefficients. So what do we do with backward pivot coordinates? We just put in a way the sequential binary partition of pivot coordinates upside down. The first coordinate is a pairwise log ratio. It compares part 1 in the numerator with part 2 in the denominator. And it continues until the last coordinate, which is actually a sort of reversed pivot, which involves one part compared to the rest. So again, the same idea. You choose a pairwise log ratio which you are interested in. By permutation, you arrange the numerator as the first part and the denominator as the second part, and you complete the orthonormal basis. You could do it in any way, as long as it is orthonormal, but the easiest thing is to include one more part at each coordinate, as it is done this way. And you run the analysis and you interpret the result of this first coordinate, which is the pairwise log ratio you want to interpret. You permute the computation, you put another component in the first part, another component in the second part. These are the ones you are going to compare. You build another orthonormal basis, you rerun the analysis, and you collect the results of the first coordinate, which is the one you want to interpret, and so on. Since this is a balance, it has a scaling constant here, but in all other respects is a pairwise log ratio. So if we have a normalizing part which we are interested in, we place it in the second position, and we permute all others. And so we can have as much as d minus 1 coordinates with the same normalizing part. So what do we get? We get an equivalent to additive log ratios. We choose a normalizing part and we compute the log ratios of all others with respect to it. But we could also change the normalizing part by permutation. Each part could also be the normalizing part. And so we could select as much as d times d minus 1 coordinate systems. But we are not violating the dimensionality, because each of these coordinate systems has exactly d minus 1 coordinates. And this is where the name of backwards pivot coordinate scheme comes from. The idea of compiling orthonormal basis in which one of the coordinates is of interest to you. This is the only one you interpret, You rerun the analysis as many times as you want, but you build the sequential binary partition in reversed order to ordinary pivots, and so this is why we say backwards pivot coordinates. Let's see an example. If we have three parts, we can have as many as 3 times 2. We can have as many as 3 times 2 pairwise log ratios, yeah, but some are an inverse of the others, and so really you can have only 3 distinct ones. If we have 3 parts A, B, and C, we can have a pairwise log ratio between A and B, between C and B, and between A and C. And this is the balance corresponding to the comparison of A and B. And we need another coordinate which is orthonormal with respect to the first, which is the balance between the geometric mean AB over C. This would be one of the coordinate systems. If we run the analysis with this coordinate system, we get the results regarding this pairwise log ratio. But we can repeat this as many times as we want. We can build also this coordinate system, and we get the log ratio between C and B, and the missing orthonormal coordinate to complete the system. Actually, if we have these two, we get the same as if we have the ALR additive log ratios with respect to B. I mean, we get the same in terms of interpretation, in terms of results, not always. And this is why we build all these systems of coordinates. Sometimes the results are not the same as when you use additive log ratios, or when you use pairwise log ratios as they are. So our addition is to complete an orthonormal basis around the pairwise log ratio. And this is important for some statistical methods. So some statistical methods indeed rely on orthonormal coordinates in order to be correct. We focus on 2 particular such methods: principal component analysis and regression models in which the composition is explanatory and the real variable is dependent. Let's just start with regression. So, in principle, regression is an affine equivariant method, at least ordinary least squares is, and some other estimation methods are as well. It's an affine equivariant method. So why should it be a problem to have pairwise log ratios? I mean pairwise log ratios as oblique coordinates. The problem is that when you use oblique coordinates, the interpretation of a coordinate does not correspond only to its construction, but you have to follow the rule, keep all other regressors constant. So the interpretation does not only depend on the own formulation of the coordinate, but it also depends on how the remaining coordinates are built. But the most serious consequence for practical purposes is that interpretation is not as intended. Interpretation is not the effect of a trade-off between 2 parts. It's not the effect of increasing just one part at the expense of reducing just one other. Let's see it. This is a toy example. This is one of these lovely simulated data sets provided by Atchison in his book, which is called Coxite in honor of Cox. Well, the data set is larger, but we consider only three minerals, which Atchison calls ABC, albite, blandite, and cornite, to explain porosity of the rock through ordinary least squares regression analysis. Let's imagine that as researchers, we are interested in the trade-off between albite and cornite. What happens with porosity when you increase albite and reduce cornite? Well, we need d-1 log ratios, so 2 log ratios. If we use pairwise log ratios as usual, as oblique, we have several possibilities. We can use albite and cornite over cornite together with blandite over cornite, and albite over cornite accompanied with albite over blandite. There are only these two possibilities. You would also permute numerator and denominator. So if you don't, that's it. You have only these two possible models using pairwise log ratios. Well, here are the results. Estimates and standard errors within parentheses, and we have the same log ratio, but with different results. But this should be not surprising, because we are keeping constant something else. And when we interpret a regression with oblique variables, we always have to take into account what we are keeping constant. So, if we increase albite over cornite here, we have to keep the ratio of blandite over cornite constant. It means that blandite will move together with cornite. It means that you're actually increasing albite and decreasing cornite and blandite together, not only cornite. While here, we are measuring the effect of increasing albite and blandite together and decreasing cornite, because blandite is forced to increase together with albite, because this variable here is kept constant when you interpret the other variable. So we do not manage to get what we want when we use pairwise log ratios. When we use pairwise log ratios, normally we want to measure the effect of trade-offs of increasing just one part and reducing just another. Now, the first model before was actually an additive log ratio model. It contained all possible log ratios with, if I remember well, with cornite as the denominator. Well, here we have another possible additive log ratio representation with albite in the denominator. We still compare cornite with albite. We have only permuted numerator and denominator. So we would expect to get the same results as before, only with a reversal of sign. And this is not the case. This is not the case. We get completely different point estimates, standard errors, statistical significance. and so on. Even if all three models have the same predictions, have the same Cook's distances, they have the same global F statistics, they have the same R squared, they have the same adjusted R squared, so they are equivalent models in one way, in some way, but the interpretation is misleading, counterintuitive, even we can call it contradictory if we permute the numerator and the denominator and we do not get the same. Now, how would it look like done in the way we suggest? So with backwards pivots. We take the log ratio we want, the one we're interested in, and we take it as the first coordinate in an orthonormal basis, and we complete the orthonormal basis with the necessary remaining coordinates, and we run the analysis, and we come only to the interpretation of this. What was the problem before? The problem before was that other parts were increasing together with albite, or other parts were increasing together with cornite. Well, the other part here is Blandite. When we keep this constant, it means that Blandite does not increase together with albite or with cornite, but stays, say, in the middle. It keeps proportional to the product of both. And this is why now we can interpret this really as a trade-off only between albite and cornite. What happens to the dependent variable when we increase only albite at the expense of decreasing only cornite? Well, in general terms, we would have a regression model looking like this. This is the first coordinate, which is a pairwise log ratio, completed with d minus 1 coordinates, which form an orthonormal basis, and only the first coefficient is interpreted as the pairwise trade-off between the first part over the second, and by permutation, any parts you want. You get the estimate of this. For each time you run the model for each pairwise log ratio you want, you compile this in a table, and all the rest you can take from anywhere, because the intercept term is always the same, predictions are always the same, the overall model statistics are always the same. So we said we are going to study two statistical methods for which we think that our approach can be particularly useful. One was regression, another one is principal component analysis and the corresponding compositional biplot. To begin with, what do compositional biplots have to do with pairwise log ratios? The usual compositional biplot does not use pairwise log ratios at all. The usual compositional biplot uses CLR coefficients. And each arrow in the compositional biplot is a CLR coefficient. This is the normal biplot, the usual biplot in compositional data analysis. We have to admit that you can compute a biplot from anything you want as long as it makes sense. And in some cases, it has been found appropriate to represent pairwise log ratios in the biplot. So to see the pairwise trade-offs directly in the graphical representation. And this is what is done in several works by Greenacre, but not only by we focus on the second option. You know, what happens if we want to have pairwise log ratios as arrows in a composition, as rays in a compositional biplot. Again, the results will depend on how we arrange the pairwise log ratios. Because the principal component analysis is a method which is based on distances. Distances depend on how you choose the pairwise log ratios. So if you would choose a different pairwise log ratios, you would have different scores, and if you have different scores, you have different everything, distances, loadings, everything. So Klinchova and others introduced the idea of pivot coordinates into biplots, and we do the same but with backwards pivots. In this way, we can use biplots based on pairwise log ratios, but scores and loadings will not depend on the pairwise log ratios we choose. Again, it's a matter of rerunning the analysis several times. The scores will be the same, so you can get the scores from any of the runs. And from each run, you get the loadings of the first coordinate, and you put all these loadings together in one single graphical representation. Now let's see a quick interpretation. This is about sediment compositions in the Gallart River in the Czech Republic. These sediments were collected downstream of an industrial city with CoDa factories, production of batteries, cars, and motorcycles. And so the upper strata of the sediments are contaminated as a result of this. We are also interested in grain size, and we take the 50th percentile of size as a measure. This will be the dependent variable in regression. We have several elements, and we choose aluminum and silicon as normalizing parts, so they will be the pairwise log ratios. Now we start with regression, and we study grain size explained by the natural, so the lithogenic elements: aluminum, silicon, potassium, titanium, rubidium, and zirconium. And we use pairwise log ratios twice, as additive log ratios and as backward pivot coordinates. As we said before, we use aluminum and silicon in the denominator. So we run the additive log ratio model twice. And the backward pivot coordinate model more than twice. Once for each possible pairwise log ratio. We have compiled the results in this table. Let's just choose one of the trade-offs as an example. Let's choose the trade-off of silicon over aluminum, or of aluminum over silicon. It should be the same, or no? With additive log ratios, or as backwards pivots coordinates. We again set these two log ratios. We start with backwards pivots because we know in advance that results will be coherent, and indeed they are. When we reverse the numerator and denominator, we get the same result with a different sign. Both are statistically significant. So increasing aluminium while decreasing silicon decreases grain size, or increasing silicon at the expense of decreasing aluminium, of course, increases grain size. But when we use the additive log ratio representation, it's a mess. Results change, significant changes, and even results stand in contradiction when you do a permutation of numerator and denominator. So it looks as if increasing silicon and decreasing aluminium would have a significant effect, but increasing aluminium while decreasing silicon would make no effect at all. Of course, this contradiction is there because we do not interpret the coefficients properly. We are actually not decreasing only silicon, and we're actually not decreasing only aluminium here. But here, yes, here we are increasing silicon and decreasing only aluminium, or increasing aluminium and decreasing only silicon, and this is what we want, supposedly. Now that we continue the example with principal component analysis, we have added some contaminants, copper, lead, and zinc. We keep the natural elements of before. We keep using aluminium and silicon in the denominator of the pairwise log ratios, and we run the analysis actually 4 times. Okay. So we have 4 biplots to this side with additive log ratios, to this side with pairwise log ratios, or with backwards pivots, sorry. In the upper part with aluminium in the denominator, in the lower part with silicon in the denominator. There's a double coding of cases. Numbers mean the sampling points, the drilling points, and colors mean depth. Green means closer to the surface, where we expect to find the highest contamination, and brown means deeper samples. Now we start here, which we know in advance it will be correct. We have the first axis dominated by depths, and lower depths at the right. Here also, well, of course, because the scores are exactly the same. And we also have the contaminants, zinc, copper, and lead, to the right of the first axis, and here as well. Well, copper is actually under zinc, but it's also there. Here we have silicon with aluminium in the denominator, so the pairwise log ratio between silicon and aluminium. And here we have aluminium over silicon. It has to be in the opposite direction, and it actually is in the opposite direction. When we go to the additive log ratio representations, the scores do not keep the same, and interpretability is a matter of luck. So here, still we have an axis which is related to the contaminants and related to depths. Here, not even that. Actually, this is definitely the worst representation of the 4 representations shown here. But it was just a matter of a choice part in the denominator, which make it bad. So you really cannot trust this kind of results. It's just permuting the log ratios can lead to such big differences. So, to conclude, simple pairwise log ratios are well liked. They are conceptually easy. Interpreting what happens when you increase one component and you decrease another is extremely appealing. And so the earliest and simplest log ratios, what we call additive log ratios, are still used. While advances in the methodology have brought more sophisticated alternatives, which in some cases are difficult to interpret, not always, in some cases. So what we try to do in this article is to bring both developments together, to have the simple interpretation together with the robustness or reliability of orthonormal log ratios. So it's a way, as a way of understanding Occam's razor rule. So we try to use simple tools, so we keep using pairwise log ratios, but not simpler. So we keep the trustworthiness of orthonormal coordinates, which is important for some statistical analysis, maybe not for all, well, definitely not for all. Some statistical analysis methods give exactly the same results with orthonormal or with oblique coordinates. But, well, if you use orthonormal coordinates, it's a guarantee that things cannot go wrong. I have asked Martin to share the slides with you, and here you have the key references of the article. So if you are interested in the issue, this would be the way to start with. And well, thanks very much. My contact details are also in the last slide, so you can. I will be happy to interact with you on this topic, and all other co-authors also will be extremely happy to. Thanks very much.
Thank you very much, Germà. Thank you very much to fit the timetable of the seminar. And yes, the slides and also the talk was recorded, and we provide both the slides and the recorded. Well, thank you very much to all of you. And it's time for short questions. You turn on your microphone and you say to Germà the question that you want. Is there any question?
I've got a question.
Yes, please.
Germà, thanks for the talk and for the paper with Carl and Peter. I read the paper, and there are some aspects that really raise interesting questions and something that really surprises me. You probably know that I and some colleagues for several years have been echoing criticisms made by John Aitchison himself about the isometric log ratio transformation, about the balances, which we find are unhelpful to practitioners. And we've been advocating simple pairwise log ratios. Now, I read on your slides and I read in your paper, the resulting coordinates from balances include some that do not have a straightforward interpretation, if any at all. In such cases, their practical usability is questionable, so they turn out to be less appealing for geochemists. This is exactly what we've been saying for a long time, and we've been heavily criticized for saying it. So my question is, with interesting alternatives that are being presented, are we finally and hopefully witnessing the death of the isometric log ratio balance in favor of simpler, more interpretable, and more helpful transformations for the users?
Well, thank you very much for the questions and for the personal compliments. I don't think we're going to witness the death of anything. Say you know better than me that science has its own inertias, and well, it's a matter of the laws of evolution a little bit. So new species, so forms of computing log ratios appear, and then there will be a natural selection, and well, the scientific community at large will decide which methods are more practical or more useful or more correct or more liked, and we will see which way of computing log ratios will prevail, or maybe none at all. Maybe these alternative methods will still coexist for a long time. I don't think if I can say anything more about that, but well, indeed pairwise log ratios are especially appealing, and we should find ways to make them fit both from the point of view of practice and from the point of view of theory. Thanks very much.
Well, is there any other question? Please, yourself.
Can I?
Yes?
Okay, thank you for the presentation. I have just one question. I was wondering if there is necessary, if it is necessary to adjust the p-values in the regressions for multiple comparison.
Sorry, I'm not sure I understood you. To adjust what? Can you repeat the question?
P-values in the regression models.
Exactly.
P-values. Well, that would be indeed be helpful. What I keep wondering is if you use the Bonferroni correction, which is the easiest, what would be the proper adjustment to make? D minus 1, D times D minus 1 divided by 2. I would start by adjusting it by D minus 1, because actually these many log ratios are redundant with respect to one another. So at most you would be testing D minus 1 effects at the same time. So I would suggest that you divide alpha by D minus 1 to start with, if this helps you.
Okay, thanks. But in your case, you didn't adjust the p-value, right?
No, I didn't.
Thanks.
Thanks to you for the question.
Okay, another question, please. It's time for another. We have time for another quick question.
Oh, sure.
No? Well, thank you very much for all to attend the seminar, and thank you very much for our speaker. Please turn on the microphone and give an applause to Germà. And see you in the next seminar. Thank you very much. Bye. 12. Vai. Para de gravar. Paro de gravar.
Bye. Thank you, Germà.
Thank you.
No pararan. No pararan. Per què no paren?
No, ves els tres puntets? Atura.
Vale.